This talk is about breaking magical barriers. The car that you see in the picture is a Bugatti Chiron, which was the first hypersport car to break the 300 miles per hour barrier, and the orange on the car it just so happens that it matches the RabbitMQ orange. But it's a very nice orange, I have to say. My name is Gerhard. I'm a staff software engineer at VMware, and I have been a core RabbitMQ contributor since 2016. And just as Bugatti has its challenge with breaking the 300 miles per hour barrier, so did RabbitMQ. The RabbitMQ challenge was slightly different in that we tried to exceed the 1 million messages per second, and I'm pleased to announce you that this year we finally did it. RabbitMQ, for those that have used it, is a very popular, maybe the most popular open source message broker, but it was never known for high scale. In 2020, for example, the maximum message throughput for a single queue was somewhere around the 50,000 messages per second mark, which, again, it's not high throughput. This year we reached 1 million, and you may be thinking, hang on a second, I thought I've heard this before. And you're right. In 2014, we did the same thing. We hit 1 million messages per second, but that million was very different from what we did this year. For starters, in 2014, we had 32 RabbitMQ nodes. It was a pretty big cluster. This year, it was just one. In terms of connections, we have 12,690 in 2014. This year, it was one publisher and one consumer. And as for queues, in 2014, there were 186 of those. So it wasn't a single queue. This year, it is. Maybe the most important factor is that the messages were not durable. They were only stored in memory. This year, they were. Before we understand how RabbitMQ achieved this, we have to go back to Bugatti. And Bugatti, in August 2nd, 2019, they have broken this magical barrier of 300 miles per hour, which is incredibly hard. Andy Wallace, the official test driver of Bugatti, he was saying how completely insane the speed is. And it's very difficult to imagine a car going that fast. This is the very moment when Andy Wallace broke the barrier of 300, and it must have felt so exciting. You see, Bugatti has been working on this for about 15 years. In 2005, they broke 250 miles per hour, and it took them 15 years to reach this new threshold, this new barrier. But why is 300 miles per hour hard? And we need to understand this because there are so many similarities as to why is 1 million messages per second hard. For Bugatti, everything starts with the engine. This is the actual engine in a Bugatti Chiron, and it's a monster. It needs to be a monster because the power required to reach 300 miles per hour is immense. If for 150 miles per hour, you need 200 horsepower, for 300, you need 1600 horsepower. So for twice the speed, you need 8 times the power. In our language, it's an ONQ problem. We all love O1, which is nice and flat. ON, it's okay, it's a bit linear, but it's okay. ONQ is very, very hard. The engine for RabbitMQ is the Erlang runtime system, or ERTS for short, and this is what it looks like. What we're seeing here is schedulers, Erlang schedulers, and how hard they're working. We can see that only the first three ones have some load on them. And schedulers, they map loosely to CPUs. They're regular schedulers and they're dirty schedulers. So in this case, we have only 16 CPUs and 16 schedulers, but 16s are dirty ones. We can ignore that for now. It just explains there are only 16 CPUs here. The other important things, the Erlang processes, is actually the things that do the work. So it's a unit of concurrency in Erlang, the process, and every single Erlang node or RabbitMQ node can have tens of thousands of those, even more, depending on how many connections and channels you have and queues. You will notice, based on the name of the initial call, roughly what type of a process it is. In this case, the first one, The top one is a file writer. It writes things, data, to disk. And the other two, they're connection processes. In this case, we sort the processes by the number of reductions. And the reduction is a unit of work. Basically, how hard is the process working? In this case, the busiest airline process is performing 36.7 million reductions per second. So that's a very high number. We can see it's by far the busiest. And when it comes to the reductions per second, the CPU frequency plays a big role in which process and how many reductions per second the same process can do. By the way, if you run RabbitMQ Diagnostics Observer in a terminal on a RabbitMQ node which is 3.8 or newer, you'll get exactly the same view. Back to the CPUs though, let's take a CPU, an Intel Xeon, where the maximum frequency is 5 GHz. In that case, the Osiris writer will max out at about 36.7 million reductions per second. And that will translate in the message throughput to about 1.4 million messages per second. Take a slower CPU, and when I say slower, where the maximum frequency is lower, the same Osiris writer will max out about 23.6 million reductions per second, which means that the message throughput will be significantly lower. In this case, it's under 1 million. Now, what I'm wondering about is, what would your CPU do? How fast is your CPU? And to do that, you will need to run 3 commands. The first one is to start the RabbitMQ broker. That's the command to run. And the second one is to start the benchmark against that RabbitMQ broker. To find out the number of reductions in the context of the RabbitMQ broker, we need to run RabbitMQ Diagnostics Observer, and by default, the processes will be sorted by memory. What we want to do is RR, enter, which will sort the processes by reductions in a time window, which is 5 seconds by default, and we change that to 10 seconds or 10,000 milliseconds, enter, and then you'll see exactly the same view that we had before. This will tell you how fast is a RabbitMQ stream on your CPU. Okay, we talked about engine. The next thing, which is very important, are tires. The tires, you see, they're the only element of a car which touches the road. It's the only physical contact that the car has with things around it. Body as well, but that's slightly different. This is hard contact. In the case of a Bugatti Chiron, the tires are very special, and they have to be to deal with the force, with the rotations per second, with the speed. The only way they can be so strong and deal with those forces is they're carbon fiber reinforced. Carbon fiber, you see, it's 10 times stronger than steel, and it's 5 times lighter. So it's light and very strong. And as amazing as they are, these tires, they top out at 318 miles per hour. The car, if it went faster, the tires would blow out, there would be a big crash, and most probably the driver would die at that speed. Nobody wants that. So how do these tires compare to RabbitMQ? Well, in RabbitMQ, and of course other systems as well, you have disks. And disks have typically just one, right, when it comes to writing messages. You can have more, but not for a single stream. You'll only have really one disk. And you all know that rotational disks or HDDs, they're slow. Everybody likes solid state disks. And they tend to be 10 times faster and significantly, maybe 100 to 200 times faster when it comes to random writes. NVMEs, they're also solid-state disks, they just have a different interface. They are 10 times faster still than the SATA disk or SCSI disk. How do streams work with the different disk types? As it turns out, a single stream will max out in the cloud. This is the Google Cloud, the C2 standard 16 instance. They'll max out at about 1.1 million messages per second. You guessed it, it is the CPUs. the CPU that we get for that instance type won't allow streams to go faster. And it turns out that the disk doesn't really matter. Even if you have more streams, there's a certain limit that once you reach, it won't go faster, but it's not the disks in this case. It doesn't matter which disk type we use, they're equally fast. The disks are not the bottleneck. The bottleneck is actually the CPU. That's the reason why the streams won't go faster. Now, why? Well, in the case of streams, they do sequential I/O. We have the right buffer cache, and yeah, we just do sequential I/O batching. That's the other one. I almost forgot about it. Very important. Batching. That's why the writes, when they write, it doesn't really matter what type of disk you have. However, what happens if we were to use a different payload size? In all our tests, the message payload size is 12 bytes, which is tiny. It's a timestamp. That's what it actually is. And it's not real world. A more realistic size would be 8 kilobytes. But there's a problem with that. 8 kilobytes, if you have 1 million messages per second, it translates to about 8,000 megabytes per second, which is 64 gigabits. And that's before you add replication and before you add consumption or streaming to consumers. All put together, you need a very big network to be able to service that type of traffic. Then, I'm sure you would start to see when a NVMe disk would be faster to a rotational one, because you're pushing 8,000 megabytes per second. It makes a big difference. Lastly, very important for Bugatti Chiron's conquering of that magical barrier of 300 miles per hour is aerodynamics. Basically, the air that flows around the body of a car can make a big difference as to how fast that car goes. CD, the coefficient drag, it's how nicely the air flows around the car. And you may be familiar with that, but what you may not know is that the front of the car makes a very big difference when it comes to 200 miles per hour and over. You see, at that speed, the car will start compressing the air in front, so it's a huge force that the car has to deal with. And every single tiny detail does make a difference. It's not just the front, it's also the back. If you have a big wing, a rear wing, it just creates too much drag. Also, the air will start separating around the back of the car, which would make it create more drag or make it slower. What you want is a thin and very long car at the front and the back, so that you have like that nice airflow around the car. You still need to create downforce because those are tremendous speeds, and in Bugatti's case, it creates the vents on the sides. They create downforce. You can't have a big wing. You need some way of creating downforce at over 200 miles per hour. You must be thinking, how does this compare to RabbitMQ? In this case, we have a 7-node RabbitMQ cluster, and the RabbitMQ cluster is an Erlang cluster. It's a complete graph. Every node connects to every other node, so you have a lot of connections. These links that are created between nodes, they are bidirectional, they're TCP/IP sockets, and you have one of this per pair. So not only that you have quite a few of these, but they're also transitive. So any node, once it connects to another node, all nodes that that node is connected to, the initial node will also connect to them. So you have lots of connections. INET-TCP is the default Erlang distribution, but there are others. INET-TLS, I think, is one of the most popular ones when it comes to encrypting traffic. You can do that, but it will slow things down. So for the purpose of this talk, we're only focusing on INET-TCP. We benchmarked this in 2019, and we noticed that at about 60 kilobyte payloads, the maximum that we reach is about 1.8 gigabytes. This is a synthetic test. It's not realistic. In our case, we had 100 processes, very lightweight, going as fast as they can. It's not real world. A real world maximum is more like 5 gigabits in either in one direction or about 2.5 gigabits when traffic is going both directions. That's the maximum that these links can sustain. So why does then a classic mirrored queue, the maximum throughput of a classic mirrored queue, which is replicated across 3 nodes, why is it only 15,000 messages per second? Now, these are very small messages. There's a single publisher, single consumer. Why is it so low? To understand that, we need to understand what happens in the RabbitMQ cluster for classic mirrored queues. And by the way, if you have used RabbitMQ, this is the queue type that you will be most familiar with. This is a mirrored queue, so if you haven't used mirroring, you won't have used it. This is a classic mirrored queue. So we have a 3-node cluster. The queue primary is on RabbitMQ1, and there are 2 replicas, RabbitMQ2 and RabbitMQ3. Start publishing messages. The publisher is local to where the queue is. There will be a connection process, a channel, and eventually the queue. So the messages have to flow through these 3 processes. These are Erlang processes. Remember from the engine slide. Remember from the engine section. The queue primary, to replicate messages, it has to go around the cluster. It's something called chain replication. It's a homegrown replication algorithm. It was okay, but it's very inefficient. And what it means is that the messages have to go around the ring to complete the ring. If this was not enough, the channels, they're also publishing the messages to both queue replicas. So for every message coming in, there are 5 messages that have to go around the cluster. They're using the Erlang distribution, those links, and that's very, very inefficient. Of course, we must not forget about the consumers. The consumers, they may be non-local, so there's like an extra connection going between the channel, the consuming channel, and the queue primary, which may be on a different node. There's quite a lot of overhead in a cluster when it comes to replicating the messages, as well as ingesting them and serving them to publishers. Okay, in 2019, RabbitMQ 3.8 introduced a new queue type, a quorum queue. It's also a replicated queue. It's using the raft replication, which is more efficient. The messages are durable by default, but still, the maximum throughput is about 30,000 messages per second. It's twice better, but still nowhere near a million. 1 publisher, 1 consumer, 12 byte payloads, and 3 replicas. This is very important. Also the specs for the instances and the Erlang use and Ubuntu, you can see it in the bottom of the slide. So why? Why is a quorum queue only 2 times faster, which is still good, but why? This explains it why. The raft replication, the way it works, the messages, when they go around the cluster, there's only a 2x. So from queue leader, 1 set of messages goes to the first queue follower, and then the other queue follower, the second one in this case. So we have only 2x messages going around, not 5x. And that's why they're twice as fast. Also, the consumers, they will always get messages from the local node they're connected to. Only the ACKs have to travel around from between nodes through the Erlang distribution. So how did streams achieve this 36 times improvement? This is why. The stream replication, first of all, the publishers, they have a new binary protocol which is way more efficient. So everything, both classic mirrored queues and quorum queues are using AMQP 091. In this case, we're using a new custom binary protocol. There's no channel, and the stream leader, it replicates messages to the followers using dedicated TCP connections. So that means no more Erlang distribution. Not only that, but the TCP connections are making use of send file, which makes the data transfer from data on disk straight to socket, and the kernel handles all of that. Super fast, very efficient, very low memory usage. It's part of the trick, really. When it comes to the consumers, we see the same thing. They're also using send file, which makes them fast. They're much quicker to consume messages. They're also using the binary protocol, always local delivery, and there's no channel. So publishers are fast, consumers are fast, the whole system is fast. But what made the biggest difference? the biggest difference it made the binary protocol. When we added streams, by the way, you can use the MQP NOT91 protocol, and with that protocol, with your existing clients, you will reach about 30,000 messages per second. Enter the new binary protocol, which is so much simpler, so much efficient. By the way, new clients, that's when we reach the 40 times speed up, the 1.1 million messages per second. We talked quite a bit about streams and how they work, but what is a stream? We haven't addressed that yet. In very simple terms, a stream is a durable, replicated log of messages. And that is a very simple data structure, both on disk and also what happens in the RabbitMQ node. It's very simple, and guess what? Simple is fast in this case. The one key difference to queues, and that's why we're not calling them stream queues, we're just calling them streams, is that there is this concept of message replay or time traveling. What that means is that consuming a message will not destroy it, it won't delete it from the queue. A consumer can consume the same message as many times as it wants, and it can even go back in time and say, hey, you know what? I want messages from 2 days ago, and it will start streaming the messages, which some of you will really appreciate this feature. Another key difference to queues is that streams, they are built for large fanouts. So think many consumers. The more you add, the quicker it goes. It's amazing how well this works. And contrary to our advice, we were saying that a happy rabbit is an empty rabbit and how you should keep your queues empty all the time so that things flow efficiently. In the case of streams, the opposite is true. Actually, you don't even really have a choice. As messages are published, the stream just grows. And that's okay, you can have billions of messages in the stream. As long as your disks can persist those messages, there's no problem. From a performance perspective, because of the sequential writes and the sequential reads, it's no problem. Billions is fine. Most surprisingly, the speed is an unintended feature. It's accidental, like that orange color in the Bugatti Chiron. It just so happens that streams are fast. Now, if you want to learn more about streams, tgi.rabbitmq.com, it's a place where we post videos, typically every month, about different RabbitMQ topics. By the time you're watching this presentation, the talk where we introduce streams and we go into length, how they are, what they work, I think it's about 45 minutes, you will be able to watch. So if you want to know more, that's the place to go. Streams would not be possible without these three people. All of them are core RabbitMQ contributors. In alphabetical order, from left to right, we have Arnaud, we have Diana, and we have Cara. Diana is the only team member that has an actual rabbit called Zen, and yeah, he's the youngest team member of the RabbitMQ team. But more is coming. If you think streams is it, it's just the beginning actually. Super streams, I love the term, they scale better horizontally, and they're a little bit like consumer groups if you're familiar with other streaming technologies. Erlang version 24, the next major version due out this summer, has a just-in-time compiler. It's a new feature which makes everything up to 50% faster. And this is something that was confirmed, including for RabbitMQ, by the Erlang team members. I'm very excited to try that one out. NVMe storage is becoming more common, and we'll see how we can get it in persistent disk form. Typically, they're only local disks in the cloud, but it's just becoming more common. So that's one piece of technology which will make a big difference for data structures that need fast disks. ARM, the CPU, they have way more encoders and they have way more cores. There's no hyper-threading, there's dedicated L2, L3 caches, which are amazing for a system, for a runtime such as Erlang, which can make full use of those CPUs. I think that will be a game changer, not just for workstations and work laptops with the Apple's M1 and M2 and what else is coming, but also for servers. I'm really looking forward to that too. And lastly, We do have better platforms for testing, benchmarking. We can do these things quicker. Do you actually know that when speed testing and performance started, this whole the industry started chasing quicker cars and more powerful cars, testing for cars would take maybe 7 days, 8 days in wind tunnels. Things would be very, very slow way back when. Now it just takes 2-3 hours to see what changes to the car all that computer modeling has. And the same applies to RabbitMQ. As I finish my talk, there's one thing which I cannot stop thinking about, and that is, what if you don't need a car? What if you need a rocket? If that's the case, I would very much like to hear from you if you don't need streams, but you need something else. I'm very curious about the challenges that you have, and I'm very curious about where do we meet? Where does our R&D, the RabbitMQ R&D, meet with your needs? Thank you very much.